May I request Ragavendra, our next speaker, to share his slides?
Yes, I'm sharing. So can you see my slides?
Yes, it is visible.
Okay.
So I'll remind you at 10 minutes.
Okay.
You will have
Thanks.
12 minutes to speak.
Okay. Thanks for the opportunity. Thanks, Srinath. This talk is based on my recent paper titled Accounting for Scalar Non-Gaussianity in Secondary Gravitational Waves, for which I have given the archive identifier here. So the outline of my talk will be like this. First, I will introduce what the secondary gravitational waves are and what the scalar non-Gaussianity, how we introduce the parameter of scalar non-Gaussianity and how we extend it to account it in our calculations. And then I will present a method to calculate the modifications arising to the scalar power spectrum PS due to the non-Gaussianity parameter, namely FNL. Then I will move on to estimate the non-Gaussian contributions that are arising to the observable quantity of our interest, namely the secondary spectral density of the secondary gravitational waves, denoted as omega GW. I will illustrate this method after setting this up using two representative models, and I will quickly summarize with the results obtained from these models and conclude with a brief outlook. So, what are secondary gravitational waves? Well, as we saw in our early first talk of this session by Professor Sakalaredo, these are second order tensor perturbations. These are actually sourced by scalar perturbations at the second order of the perturbation theory. And there are certain models of inflation that have enhanced scalar power on small scales so that we may actually have the sourcing to be strong enough to generate significant detectable strengths of secondary gravitational waves in the current universe. What is more interesting to note is that these models also produce non-trivial shapes and amplitudes of scalar non-Gaussianity, especially at the level of bispectrum. And the motivation of this work is to show that it is important to account for this non-trivial scalar non-Gaussianity in our computation of secondary gravitational waves. I've just presented detailed reviews in this context here under, and I will be happy to answer questions in detail. I will just present the results of my work. So the FNL is typically defined, the scalar non-Gaussianity is defined through this parameter, through this definition, where R is the scalar perturbation in real space, and RG is the Gaussian part of the perturbation, and the second term is the non-Gaussian part, where FNL sits as a dimensionless parameter quantifying the non-Gaussianity. What is interesting to note is that it is a dimensionless parameter. Also, it is independent of any scales involved in this definition. So this is the conventional definition, and we extend this definition, which is already explored in the literature, in this form, where we will consider the relation in Fourier space and consider the mode function corresponding to the scalar perturbation and decompose into Gaussian part and the non-Gaussian part, where we see that FNL clearly has scale dependence now and sits inside this integral. Now, if we are to capture the non-Gaussianity arising in a given model, especially at the level of bispectrum, we compute the 3-point correlation of this mode function, and FNL gets related to the 3-point function, namely the scalar bispectrum denoted as G and the power spectrum PS through this relation. So now we have the FNL defined along with this explicit wave number dependence. We will ask what is the modification it is going to induce in the calculation of power spectrum, namely the 2-point correlation of this relation. So if we take the 2-point correlation of this RK, we get power spectrum modified, which I denote as PS superscript M, which obviously will contain Gaussian part, which is just PS of K, and portion which is clearly a non-Gaussian contribution, or rather a correction to the Gaussian power spectrum denoted as PC of K, and this PC of K will be proportional to square of the non-Gaussianity parameter, as can be expected. So to make sense of this expansion, we will invoke this formalism of constructing Feynman diagrams, though it is not arising from an action-based method. We will just make use of the structure of integral and the expansion in the series. So if we are to associate Feynman diagrams, this first term will just be represented by this 2-point correlation diagram, and the second term is nothing but the one loop correction to this 2-point correlation. And evidently, if this PC of K is greater than the original PS of K, it implies there is a large non-Gaussian modification to the power spectrum. This is for the scalar power spectrum. Now I want to consistently account for this FNL in our omega GW due to the secondary tensor perturbations. So to do that, as mentioned earlier, these secondary gravitational waves are going to be sourced by the scalar perturbations, and that is clear when we look at the expression of the 2-point correlation of this secondary tensors, namely the pH of k in terms of the R case, as I have mentioned in the right hand side. So as you see, the 2-point correlation of secondary tensors is proportional to 4-point correlation, because it is being sourced at the second order, 4-point correlation of the scalar perturbations. And without introduction of non-Gaussianities, we can readily use Wick's theorem and reduce this into square of a scalar power spectrum PS squared in a sense. And then we can compute the dimensionless energy density omega GW in terms of this pH computed in a given model of interest. This has been well known in the literature. For instance, there are these nice papers discussing the calculation in detail. What we are interested is that we shall now introduce non-Gaussianity in this 4-point correlation, the scalar non-Gaussianity parameter FNL, in each of these mode functions sitting inside this integral, and ask what are the corresponding contributions to this pH of k, and hence to secondary gravitational waves omega GW. So obviously we can expect that we are going to get terms which are proportional to FNL power 0, which is just the Gaussian part, and then there will be terms proportional to FNL squared, FNL power 4, and so on. So that is essentially what we get. We need not get confused with the complicated looking integrals. I'm just expanding the omega GW in terms of terms proportional to FNL power 0, which is just product of power spectra, and then pH superscript 2, which I will call as pH2, which shall be proportional to FNL squared along with the appropriate wave number dependence. This is a typical expression that we will get. Of course, there will be other combinations as well. And then there will be higher order term, which is pH4, which shall be proportional to FNL power 4 along with wave number dependences. This again has been known in the literature, but we should emphasize that all the previous attempts have just assumed FNL to be a dimensionless parameter and have been treated outside the integral. We keep the wave number dependence explicitly and evaluate all these integrals along with the wave number dependence of both by power spectrum and FNL. Again, to make sense of this complicated looking expressions, we will try to construct Feynman diagrams as before. For the scalar case, I shall denote the secondary tensor perturbations as dash dotted lines, and then the solid lines as usual denote the scalar perturbations. So the secondary tensor power spectrum is nothing but the one loop correction to the primary tensor power spectrum and shall be proportional to PS squared, as can be evident from this diagram. Now I am introducing FNL, the non-Gaussianity parameter denoted by this 3-point vertex, in each of these 4 arms of this loop. And then I will ask what are the corresponding diagrams and what are the corresponding contributions. So evidently I can introduce them in 2 of the arms and get the terms corresponding to pH2. I can broadly classify the diagrams in 3 types of these diagrams as shown here. And of course, there will be multiple combinations of a given diagram based on this exchange of various arms corresponding to wave numbers. But the crucial point is that we will get 3 different contributions. And then at the level of FNL power 4, we again get 3 types of diagrams when I introduce the FNL vertex in all 4 arms of this one loop diagram. So we have set up the method to compute the non-Gaussian contributions to omega GW. What I would like to note before we look at the results is that the computationally speaking, if we are to implement this numerically, because the models involved are difficult to solve analytically, the pH2 contribution itself involves computing some 6-dimensional integrals, whereas these pH4 involve computing 9-dimensional integrals. For the purpose of this calculations, we will just restrict to pH2 diagrams and ask what is the first non-Gaussian contributions arising in models of interest. So I will just quickly illustrate this method setup so far using 2 models of interest. The 2 models are presented here in red and blue colors respectively. These models are representative models of inflation that are known to produce large enhancement of scalar power over small scales, and then produce significant secondary gravitational waves correspondingly over corresponding frequencies. So now I ask, what are the non-Gaussian imprints on these spectra that I get from these models? First, I will consider the scalar power spectrum and compute the PC of k that I encountered, that I introduced earlier. So these are the PC of k in each of the models of our interest. PC of k has been denoted in dashed lines, whereas the original power spectrum is given in solid lines. As you can see, the PC of k is significantly lesser in amplitude in both of these models of interest. And I have also attempted an analytical estimate which closely captures the feature of the numerical result in both of these cases. I've used what is called consistency relation to arrive at this PC of k, but I won't delve deep into it, but I can answer questions how this PC of k is analytically estimated. And then we proceed to ask, since this effect of non-Gaussianity is significantly lesser in terms of scalar power spectrum, what is it going to be at the level of omega GW, which is the observable quantity of interest? So if we proceed to compute that, we will compute all the three contributions that we discussed earlier, and this is the result that I get in these two models of interest. Note that I am just restricting myself to the contributions at the level of FNL squared, and there are three types of diagrams, and I have represented them in three different colors, namely light green, cyan, and dark green. What is crucial to note is that I'm focusing close to the peak of this omega GW spectra.
Ragavendra, you have 2 minutes.
Sure. Okay, thanks. And if I focus close to the peak of this omega GW spectra, what I notice is that there are non-Gaussian contributions which become comparable, if not significantly larger than the original omega GW curves in both these models. Even in this model, though they are largely suppressed, they become briefly comparable close to the peak of the omega GW. So the takeaway is that if we are computing omega GW in models known in the literature that are known to produce enhanced scalar power on small scales, it is important to account for the non-Gaussian corrections arising due to the scalar non-Gaussianity parameter FNL. So with that, I will briefly summarize the results that I have presented so far. The scalar non-Gaussianity parameter, to emphasize again, is known to have non-trivial scale dependence, and it will be inappropriate to treat them as just a number outside in these integrals involved. And if we compute the corrections to the scalar power spectrum arising due to such FNL, they seem largely negligible. However, the non-Gaussian contributions to the omega GW can still be significant and comparable to the original omega GW that we estimate in these models. So as a possible outlook, we also see that this opens up a possibility of arriving at indirect constraints on large amplitudes of FNL. If at all we have models where we get extremely large values of FNL, they can be constrained by the existing sensitivity curves and constraints on the existing the amplitudes of omega GW through the method that I just outlined. So with that, I thank you for your attention and leave you with the reference I based my talk on. So, and I will be happy to take questions, Srinath.
Thank you, Ragavendra. Other questions? You may unmute yourself and speak. Yes, Sayantan.
Yeah, thank you for nice talk. Questions to ask. So you talked about some loop contributions. So like this loop contribution that you have considered, so is it how much suppressed it is? Means it should be small, means like what is the order of that loop contribution?
Yes, that is essentially the result that I am presenting. The loop contributions are the dotted lines, whereas the original contribution, the 2-point correlations, are the solid lines that I am presenting, for instance, in case of omega GW. But what I would like to emphasize is that these are not loop contributions that are calculated in a field theoretic sense. We are just using the mechanism, using the setup of Feynman diagrams to make sense of the various integrals arising. Just because loop correction is larger in one order doesn't necessarily mean that the subsequent order corrections are also going to start becoming larger and larger. There is no clear hierarchy established as such as yet in this regard.
So in a field theoretic sense, we can't say it is like a kind of that kind of loop.
No, because these are not arising from an action. To begin with, these are not. This arises essentially from the definition of FNL that I showed here, right? So the definition of FNL, when substituted in the subsequent 2-point and 3-point correlations, can mimic the behavior of the loop corrections that we typically encounter in field theory. But this is not applicable directly in the action governing the scalar and tensor perturbation. In fact, there are works.
But in that case, you shouldn't call it a loop correction. I mean, this is not a correction then. If it is somewhere, it is large.
Yes. That is why I didn't call them correction beyond this point, because these are clearly significant contributions. So this PH2 and PH4 that I discussed, these are not just corrections. These are non-Gaussian contributions actually to omega GW. So I should clarify that these are actually significant contributions, and there are still works that are going on to understand if we can, for instance, even here, there is only pH2 that we are able to compute and arrive at the corresponding omega GW. One has to consistently account for subsequent orders as well. Yes.
Achha, I have one last question, which is
Sure.
This calculation you did from the 3-point means the non-Gaussianities in the 3-point function of the gravitons kind of thing.
No, non-Gaussianities of the scalar perturbation for the RRR kind of terms. The FNL that I mentioned is the scalar bispectrum is actually proportional to the
Oh,
3-point
this is the
correlation of,
scalar.
yes, scalar.
One.
Because
Okay.
scalars are the sourcing terms in this secondary gravitational waves.
Yeah, so I just want to make a comment. Did you? I know that observational this might be not very significant at present, which is the computing the like. I think people have computed 3-point graviton, like Maldacena and all of calculated. But there is a problem with calculating 4-point graviton correlators till now.
Okay.
I don't know that problem is resolved or not. I'm just saying this thing from field theoretic point of view. That might be a very good problem in that direction. Because the result is also not known.
Okay. Okay. It is not directly related to this work, but I will note this and follow it up.
I'm just saying that.
Sure. Okay. Thanks. Yes. Yes. I understand. Thanks.
I think we are out of time. Sukanya, is this a very quick question? Sukanya Bhattacharya?
Yes. Hi, Ragavendra.
Hi.
So can you, so this RK that you show in this slide,
Yes.
this has another contribution. So do you have a plot that shows how this RK actually behaves before, during, and after the feature in the potential?
The evolution of RK.
Yes.
So I should mention that we are calculating this after evolving all the modes. So you see that there is an integral involving all the range of wave numbers, right? So we
Yes.
evolve the modes and then compute this FNL and then perform this integral. So this is evaluated something like at the end of inflation and then propagated to the radiation domination.
So the limits in the integral are all the way up to the largest K?
Yes, smallest to largest K.
Okay, thanks.
Okay.
Thank you once again, Ragavendra, for this good, excellent talk.